Swayam Prabha. Digital India. Educated India.
Welcome. In the last lecture, we have discussed the lattice model of solutions, and then very briefly we discussed like how can we extend that to polymer solutions. So we will take it further today and then talk about the phase behavior of polymer solution using the lattice model. So what we are developing is the lattice model of polymer solutions. So again, as I have said, we will use the analogy of a lattice just to simplify the analysis. So again, it's a toy model. We are going to make similar approximations of mean field and all that. In fact, we will not completely derive the expression, they are in the books, but they are very similar to what we have done for a liquid solution. Okay. So now, one thing we noted in the last class was compared to the solution model where we assumed that solute and solvent are the same size, we can no longer assume that. Instead, what we assume is, instead of individual polymer chains present in a lattice site, we will have segments of polymer chains which are present, and these have the same volume. So segment volume is taken equal to solvent volume, and that is equal to the VC, the cell volume that we have discussed earlier. So now within that model, we can imagine that we have polymer chains. I am just drawing a line to indicate that these segments are connected, and we have done this kind of model in the context of random walk on a lattice. And of course, the remaining positions are occupied by solvent molecules. So now instead of NP and NS solvent, solute and solvent, what we do have is we have NP polymer chains of, let us say, some n segments each, and we have NS solvent molecules. And then we said that if I compare the different terms in the expression we derived for liquid solutions, what we can note here that the solute entropy and solvent entropy were the same in the case of a liquid solution, which will not be true in this case because the segments of a polymer chain are connected together. So they will have substantially lower entropy than compared to the solute which was present in the liquid solution model. So, using this idea, I said, and you can go through the detailed derivation in books, that the polymer entropy term will be divided by n, that is the number of segments in a polymer chain, solvent entropy term remains unchanged, and the solute solvent interaction term also remains unchanged. Okay. So, now one thing you can see is, unlike the earlier case where I can replace phi by 1 minus phi and we get the same expression, and that is why we said we have a mirror symmetry around phi equal to 1 by 2. This we cannot do here, because if I replace phi by 1 minus phi, we will have like 1 minus phi by n there. So, this is no longer symmetric as we had earlier. So, no, not symmetric around phi equal to 1 by 2, which also means that the common tangent is not horizontal. Okay. And in that case, we know how to find the coexistence line. So, coexistence line given by f prime phi a. Earlier we said that equal to 0, but now it is f prime phi a is equal to f prime phi b is equal to f phi a minus f phi b divided by phi a minus phi b. Okay. So, now let us go ahead and try to find the binodal, spinodal and critical point for this function graph, but we already have noted that the function is no longer symmetric. It can be anti-symmetric like this. That means it will have a common tangent that is no longer linear, no longer horizontal. All right. So, f is equal to kBt by Vc phi by n ln phi plus 1 minus phi ln 1 minus phi plus chi phi 1 minus phi. So, we can find f prime as 1 by n ln phi plus 1 by n minus 1 minus ln 1 minus phi plus chi into 1 minus 2 phi. Using this expression of f prime and using the expression for coexistence line or binodal, we can get the binodal curve from here. But let us say we go ahead and try to find the spinodal and critical point. For spinodal, we are interested in the second derivative. It is 1 by phi n plus 1 by 1 minus phi n minus 2 chi is equal to 0 for spinodal. So, this gives me a spinodal expression as chi s is equal to sorry, there is no n there. N only appears in the first term. So it is 1 by 2 1 by phi n plus 1 by 1 minus phi. Now for the critical point, I should go to the third derivative. So this gives me 1 minus phi by phi square is equal to n, which we can solve, and we will have 1 minus phi by phi is equal to root n. Again you can try putting a minus root n there. So essentially we will have phi is equal to 1 by 1 plus root n, that is the critical value. Let us see what happens when we use a minus value. So phi comes out to be 1 by 1 minus root n, which is less than 0 for n higher than much higher than 1. That is the case here. So anyway, we can pretty much forget about this solution. And then if I want to find the critical solvent quality, I can simply plug in the expression of phi c in the expression of the spinodal, and what I do get is this. Something of this sort. Okay, so the chi c will then be something like this. If you look at these terms, then for large value of n, what you can see that the first term is anyway much smaller compared to the second term. So we can drop the first term. In the second term we have like 1 by root n plus 1. 1 by root n is anyway small because n is very high. So what do we get is chi c roughly equal to 1 by 2. If I now look at the phase diagram for a polymer solution, there is two things to note here. That the critical volume fraction, which was 1 by 2 for the case of a liquid solution, is now something like 1 by 1 plus root n, that is very small compared to 1 for n larger than 1. Actually it becomes 0 in the limit n is infinite, and the critical solvent quality, which was 2 earlier, is now 1 by 2 for large value of n. Actually it approaches there for, I would say, even substantially smaller values like 300 or 200, then also you will get a value very close to 1 by 2. So with these two things, if I look at the phase behavior, the first thing to notice is it is going to be highly unsymmetric, then the critical point chi c is 1 by 2 and the critical volume fraction is like 1 by 1 plus root n. Actually we can say chi c is approximately equal to 1 by 2, and again we can have n is binodal. So here is my binodal that I have to get by solution of the coexistence curve equation, with the only detail here that the common tangent is not horizontal. Then this is my spinodal that we have derived, and this is of course my critical point. This is my metastable region. This is also my metastable region, and this is my unstable region, and below this value we of course have no phase separation. In fact, then this value of 1 by 2 has a very important meaning in the polymer language, because if chi is less than 1 by 2, I call my solvent to be good. If chi is much higher than or higher than 1 by 2, I call my solvent to be poor or bad, and if chi equal to 1 by 2, then this represents what is known as a theta solvent, that is in between the good and poor limits. Just like what we showed for a single chain, we can now think at a thermodynamic behavior level that the good solvent will be when we will have no phase separation. Bad solvent or a poor solvent is when we will have a phase separation, and a theta is just at the brink of those two extremes. So it turns out that if I now want to look at different kinds of polymer system, of course we can go through the full derivation, but just looking at the expression we began with give us good clues to derive expression for different polymer systems, even different from polymer solutions. So let's say for instance I am interested in the behavior of a polymer melt So polymer melt contains only two species. You have polymer A of volume fraction phi, polymer B of volume fraction 1 minus phi, and we have no solvent. Let us say the polymer A has Na segments per chain, polymer B has Nb segments per chain. We can build the expression of F by simply writing the entropy and interaction terms just like we did for a polymer solution. So the entropy of polymer A is of course written as something like this. Entropy of polymer B is also reduced similarly by a factor of Nb, and since we do not have any solvent in the system, we do not have to worry about the solvent entropy. And then of course we have a chi. This is no longer the solvent quality, it is between A and B, so I can call it chi AB, that represents the energetic interaction between polymer A and polymer B. And then I can go ahead and try to do the calculation of binodals, spinodals and critical point for the polymer melt as well. So by this way the very simple idea of a lattice model can be extended for different kinds of polymer systems. Although we have limited ourselves to only two components, we can think of three components as well. So now you will have three entropy terms, and you may have various combinations of the energetic interaction terms. So let us say if we have A, B and C now, we can write like KBT by VC phi A by NA ln phi A plus phi B by NB ln phi B plus phi B phi C by NC ln phi C. But then we also have to include the chi terms, and now we have to look at various combinations of the species. For example, we will have a chi AB phi A phi B plus chi BC phi B phi C plus chi CA phi C phi A. So, this is the benefit of the TWI model, that it allows us, it provides us an easy way to construct the Helmholtz free energy density of my polymer systems, and using that, by the math that we have done, we can go ahead and try to find the binodals, spinodals and critical point, and we can actually draw a phase diagram of the sort that we have discussed here. So, I will provide some examples in the course that you can work through and try to apply the same concepts that we have just used here for somewhat different types of polymer systems. So, with that I conclude. Thank you.